So, I'm Romilly. I've been a fan of the Raspberry Pi really since it came out. And recently, of course, we've seen the Pi 5 and a lot of hats that allow you to attach quite phenomenal amounts of storage. And so I decided to do a bit of an experiment and see if I could scratch a long-standing itch while I did it. Let me share my screen. That showing up okay? Screen visible okay? Okay, good. Um, so there's a tool called the Semantic Scholar, which I've used for years. There's a quite a wide range of stuff I'm interested in to do with AI and psychology and learning. And in order to track down interesting papers, I make a lot of use of Semantic Scholar. And you can do a search in their web-based interface, and it'll come up with information a bit like what you can see on your screen. This is actually a particularly irrelevant example, but it just happens to be one that's written by somebody I know. And if you take a look at what's on the screen, it describes the title of the paper, the people who wrote it, where it was published, when it was published, topic it covers, a bit more information, including a link to a PDF if one's available. And then down at the bottom, it doesn't look quite as important as the other stuff, but actually it's vital. Semantic Scholar keeps track of two really important things. One, all of the references in the paper, so that if you want to find out the background to the paper, you can identify all the papers that it quotes. But even more useful, that screen says that there are 4 citations. In other words, since that paper was published, there are 4 papers that have referred to it. And looking at those can help you keep up to date with whatever has happened since the paper was published. And there are several different ways of accessing it. But what you're accessing is absolutely huge. They've got details of over 220 million papers, and they've got details of 2.6 billion references. So an awful lot of data, and it gets updated pretty promptly. It's free to use. Just now I mentioned that quite often use it from a browser. There's also a web API which allows you to access their data from a program using HTTPS. And they will also allow you to download a local copy to run on your own hardware. And there's really a couple of reasons why I was keen to run a local copy, and in particular, a local copy on a Pi. First was performance. I use the web interface, the web API quite a lot, and so do an awful lot of other people. And as a result, there are fairly strict rate limits imposed. And even if you stick to the rate limit, if you're trying to access their data at a very busy time, you'll get a limit, you'll get a 409 error, which basically tells you to back off and wait a while before you issue an API call again. And at times that's quite frustrating. Another good reason is that there's some stuff that I wanted to do that required a lot of rapid access to the data. I wanted to be able to see not just what papers had cited one paper, but the papers that had cited them and the papers that cited them, and to display all that in a way that I could easily navigate. Doesn't apply to me, but another good reason to have a local copy of the database is that some organizations don't want other people to see what they're researching. And then the last thing, which was particularly important in relation to the Pi, is that there are an awful lot of places that would like to be able to access this data, but they don't have very powerful hardware, and they may only have intermittent internet access. And with a copy on a Pi, you can maybe swallow the weekly updates which Semantic Scholar produces, and the rest of the time you can access their entire database on a very inexpensive local machine. Total cost of the hardware that I'm using, I think, is under £300. And it's only that high because I've got a very large NVMe disk. What I'll be covering are some of the challenges I met when I tried to get this massive database on a Pi. And I'll talk about how I solved them. I'll give you a quick look towards the end at the citation graphs, the thing that I wanted to create. And we'll also take a quick look at performance. Performance has really been quite surprising. When you initially load the data sets, clearly you're loading about a terabyte of data, and it takes a while. It would take a while on pretty well anything. On the Pi, it takes about 2 to 3 days, but you can leave it running unattended for particularly for the big downloads and database insertions. So that's pain that you have to take once, and then it's done. What's surprising in a good way is that once you've got the data into the database and the database is properly indexed, it's amazingly fast to do searches on the data. If all you want to do is bring up the key feature of a particular paper, you're talking about milliseconds. And if you want to find all of the papers that cite a paper you're interested in, and all the papers that cite them, and all the papers that cite them, I had one particular example where that ended up fetching 5,000 papers, and it took about 3 seconds to do it, which I think is fantastic. When I started working on the project, first step was to pick which data sets I wanted. As we'll see in a minute, you don't, for the things that I'm doing, need them all. Those get downloaded once, and what you get when you download them are an awful lot of quite large gzipped JSON files. And then I planned the next step. I would insert that data into tables in a Postgres database, and I'd be using Jupyter notebooks to access that data and do queries. And I think now I'm using it so much that I'm almost certainly going to build a graphic user interface that will allow me to search without having to run Python or SQL queries. There's one bit of the project that isn't complete yet. I mentioned earlier that Semantic Scholar lets you download diffs which contain all the stuff that's been added, deleted, and changed each week. And I still need to write the code to download those and update the database, but I think that's going to be fairly straightforward. Talked about the data sets. These are the data sets that I decided I needed. There's one which has got details of abstracts, the texts that give you a fairly short description of what the paper's about and its conclusions. There's a data set that contains information about the authors who wrote the papers. Vitally, there's the information about citations, where one paper mentions another. That's the real biggie. There's a rather strange data set called paper IDs, for reasons that I can guess at, but I'm not sure about. the Semantic Scholar system has two different keys for a paper. One is referred to as an SHA, a SHA, which I think is based on the SHA cryptographic signature of each paper, but everything else is linked to by a unique ID called the corpus ID. And the paper IDs table allows you to go from the SHA-based ID, which is what you see on the web, to the corpus ID, which everything else uses. And then, just as important as citations, there's a data set that contains pretty extensive data for each paper. And then there's a not particularly useful data set which has some metadata about where papers are published. There are data sets that are available, but I didn't use them because they're very big, they're specialized, they weren't needed for what I wanted. And in particular, one of the data sets, so two of the data sets are to do with embeddings, which would be very useful if you wanted to type a general query and find all the papers that matched it. But there's no way that you could do that quickly on a Raspberry Pi. You need some pretty beefy hardware. And at some stage, I'll probably explore doing that on a rather more powerful NVIDIA Orin machine. So I started out with a Pi 4 with an external database. I did the code on the workstation. I downloaded my data on my workstation and then uploaded it to the Pi, and it was very slow. I ended up with the code and the data running on an 8 GB Pi 5. I've got a Pimoroni NVMe hat, and attached to that is a 4 terabyte NVMe based SSD. And as I mentioned earlier, that really runs pretty fast when it comes to queries. Started out by populating the papers table, and basically what you've got to do is unzip the JSON, and then for each row in the file that's got JSON in it, transfer that into the database, into the papers table. And when I started out, it was hideously slow, for reasons I'll explain in a minute. These days, it's running about 200 times, a bit better than 200 times faster than my first attempt. And I learned a lot about tuning databases in the process. First one is a pretty obvious lesson. If you've done much with databases, you will know this already. I did. Interestingly, ChatGPT didn't. One of the things I should have mentioned is that for a lot of the code, I spent a bit of time explaining what I wanted and let ChatGPT write most of the code. And that's actually worked very well, except that its very first version of code to update the database did a commit after every insert, and that was incredibly slow. All the obvious ways of speeding that up helped, but I ended up using what various websites recommended, and I've used it before very successfully. The driver that I use to access Postgres from Python is called psychopg2, and it has a useful method called copy from. And so long as you're inserting stuff into a database and not doing anything else and not checking for duplicates or key failures or anything of that sort, basically you give it a big file and it just whops the whole of that file into the database table in one go. Well, yeah, it's obviously doing it sequentially, but it does it very, very fast. There are a couple of complications, which I'll mention in a minute. but that's worked very well. And the third big lesson, if you've got a lot of data to load and it needs to have an index, do not create the index before you load the data. Do it afterwards. That graph shows why. If you take a look at the blue line, what I'm doing there is timing each block of about 1 million updates into a table that's already indexed. And you can see that the time is climbing up quadratically as the number of records grows. And it's also extremely unpredictable. But it's bad news. And I stopped after I'd inserted 14 million records, because it was quite clear that putting a whole lot of data in was likely to take about a year, which didn't appeal. By contrast, the orange line shows how long it takes if you're inserting the records into a table that doesn't have a key, and there's still a little bit of variation, but it's shows no growth at all. And once you've finished, you then have to create a key, but creating a key in a table that's already populated is relatively fast. It knows how to do that very efficiently. So it's a much, much better way of doing things. I mentioned that I was using copy from rather than insert. It's faster than doing a batch update, which PsychoPG2 also allows you to do. The downside is that it absolutely has to have data in CVS format. So the first thing I tried was read an entire JSON file and then write it out as CSV. And that failed on the Pi because the files are too big to fit in memory. So what I ended up with was creating a Python file-like object which maintained a buffer of the lines and asked for them to be converted from a generator, which read the original JSON. And if that sounds complicated, when I thought of it, I decided it was too complicated for me to write. So I asked ChatGPT to write it for me, very carefully specifying what I wanted, and it did it, and it worked first time, which is pretty amazing. So I've just spotted a question in the chat. Did I profile why the Pi 5 was much faster than the Pi 4? Well, there are 3 reasons for that. The Pi itself, the processor, is a lot faster, but actually most of what's going on is not processor bound. The 2 bottlenecks on the Pi 4 were the route to the solid state drive, which was an external drive on the Pi 4 and an NVMe drive on the Pi 5. But also, I made a really stupid choice of the Pi 4 because that particular Pi 4 has a power on Ethernet hat, a power over Ethernet hat, which is connected to a very slow Ethernet connection. So absolutely everything was against me. But yeah, and the Pi 5 is really a lot better for this job than the Pi 4 was. So I got all the data. I've got all the data loaded on the database, and now I've started using it. And typically the process that I go through for the kind of stuff that I'm doing involves me starting out with some interesting paper which I found via the web, and then I'll use Semantic Scholar to tell me what the paper's SHA is. And then in the Jupyter notebook, I find the paper's corpus ID, and then I got some code that will find the paper's citations and their citations, and on I go until I don't find anything new. Technically, that's a transitive closure. And then finally, I draw a nice picture showing how all the papers are related. And one of the first ones I did was a paper where the paper is fairly recent. It's highly specialized. I restricted my focus to the citations which Semantic Scholar thought were highly influenced by the paper. I ended up with a very manageable small set of things which get plotted by the software very nicely. You can see short forms of the title there. Under each paper is in a box in which you can see the year of publication, and the arrows show you what refers to what. So there are 4 papers that refer to the original one, and 2 papers refer to one of the intermediate ones as well. So quite a lot of information there, but it's a very simple example. Very easy to build. That's the Jupyter Notebook page that does it, does some imports, connects to the database, finds the corpus ID from the SHA, and then finds the links and creates a dot file, and then uses the graphviz dot program to convert that to an SVG. And it's the SVG we're looking at. However, most examples aren't quite that simple. So I thought what we'd do, I think I probably need to reshare the screen so you can see the demo. Is that looking okay, Richard?
Yep, we're good.
Yep, good. So fairly similar, load stuff, connect to the database, find the corpus ID, find the details of the paper, do the links, and then write the dot file and convert it. Let's run that. So I'm going to click Run All, and it's finished. So let's take a look at what came out. Going to open that in Chrome. That probably means I need to unshare and reshare the screen. Just organize things a bit. And as you can see, there's rather a lot more information being displayed. It's fairly clear still that there are papers and what year the papers were in and what referred to what. But the really cool thing is that if I put my cursor over a paper, it shows me the title and the authors and when it was published. And if I right click on it, it opens the paper in Semantic Scholar. So that has been a really useful tool for me, and I hope it's useful for other people. I've got at least one user already, and maybe get some more. And I think it's got quite a lot of potential. There's a lot more that I want to do to it as well. So let's reshare for the final foil. And you can see the project. It's open sourced on GitHub. It's already there. It's got code and setup instructions. I'm the only person that have tested those so far. So if anyone does want to give it a try and is happy to wait for the 3 days, then do go ahead. I am planning on trying to create a Docker version, which would be very much easier to set up and install. But I'm not sure how soon I'm going to be able to get round to that. Okay. Any questions? Oh, Andrew, that's interesting. Andrew's saying in chat that he's found a nearly 8 times speed improvement on the Pi 5. Yeah, and that confirms my impression. I hadn't done as specific measurements as that.
Very good.
Any other questions?
Yeah. So what have you actually found then? So when you run these searches, do you find like there's one paper that's like particularly important to all papers, or it's like, sort of like it's referenced by everyone and it's spawned a bunch more research, or what do you actually find when you...
I mean, it depends very much on what you're looking at. But one of the things that I should probably explain a little about the areas that I'm researching in. Some of it is to do with AI, some of it is to do with psychology, some of it is to do with the way that people learn. And I'm not an expert in either of the last two areas. I'm not even an expert in AI, although I've been playing around with it for a very long while. And quite often I'll start by reading a book, and a book will quote an interesting paper. And that interesting paper will be a good starting point. But then the two questions are, what research preceded that? And how much can I rely on it? And what's happened since? And for most of the papers that I'm looking at, the problem is that there's even more than there is on the screen we just looked at. And so actually the next thing that I'm going to be doing is finding ways of limiting the amount of stuff that's shown really to the papers that are still being actively quoted. And the next step after that is to start trying to use AI to pick out the papers that are particularly relevant to the question that I'm trying to answer. But yeah, I mean, I've found a lot of absolutely amazing stuff already that I didn't know anything about. I've also hit one or two snags. I read today the debate that's going on between Jan LeCun and Elon Musk. And Jan made a reference to a paper that he wrote a long while ago. And I thought, I'll take a look at that and see what happens if we do the citation graph. And after the backlog of papers which the program needed to sort through got to 250,000 papers, I thought it was probably time to call a halt and try something a bit more restrictive. Peter Benyon's asked if the database is divided by subject. It's not divided by no. There is a field that contains the subject, but it's pretty broad. And one of the things which you can do online is get it to get Semantic Scholar to find papers that are relevant to a subject, and then I can swallow that into my application and start exploring them. Link to the GitHub repo. Yeah, let me copy that from the file, and there it is. I will put up a PDF containing the slides and a rough script tomorrow. But that link would be useful now.
Cool. Sounds like a very fun project, actually. So what's your GUI going to look like then? Is it have you plotted that out? Have you designed that?
Yeah, I've the thing that I've been focused on is how you filter stuff for the citation graph. So the basic idea is that you can just copy an entire URL from the web-based interface, pop that into a field on the GUI I'm building, say whether you're only interested in influential citations or all citations, specify a limit on how deep the search should go, specify whether you want references or not, and then maybe filter on something that's called citation velocity, which is a measure of how fast people are citing a particular paper.
Hmm.
So that if they're citing it very frequently, it's a sign that the paper is probably interesting, at least to them, and maybe to me. And then once you've done that, it will just display the graph in the top pane.
So
But
why
for
is
the
it velocity?
rest, I plan on more or less reproducing the interface to the web interface that Semantic Scholar has already, apart from the bits that I can't do because of the much more limited hardware. I mean, they're running on real heavy-duty hardware, so that the kind of AI-based search they do is going to be quite tricky to replicate here, although I think it may be possible.
And do you have alerts and things like that? So say this suddenly this paper is getting quoted a lot, or
I get them from Semantic Scholar anyway. That's one of the services they offer. So luckily, I don't have to do that.
and is that a subscription service, Semantic Scholar, or is that?
No, it's all absolutely free.
Uh-huh.
And really, that's the reason why it's rate limited, because it's incredibly popular. And there are a number of external services that give access to it, but quite a lot of those are freemium or paid.
And is this project interesting from a software engineering point of view? Like, do you find it? Do you find like a difficult or reasonably good challenge for your software engineering skills?
It's some bits are quite tricky. The bit that was based on turning a generator into something that looked like a file was tricky, but luckily ChatGPT is a bit smarter than I am. The bit that did the transitive closure, again, I think I said exactly what I wanted, and PyCharm's AI wrote that for me. The main decision that has made it much easier is that I've used what Alistair Cockburn would call hexagonal architecture, in which all of the interfaces to the world outside my code go through well-defined interfaces which you can easily mock and easily replace and test. And that's absolutely essential, because
Yes,
you're dealing with both the I have quite a lot of code that interacts with their web API, and of course you're interacting with the database. You've seen that style in the Lazy Doro code, and it works well for embedded applications, but it works well for stuff like this as well.
Very cool. Any other questions from anyone? Nope. Okay, thanks a lot, Romilly. It's great to
Okay,
have you back. Great to see you.
thanks. That's good.